The night shift at the Cambria Iron Works began at 8 o'clock, when the day crew handed over their tools and walked out into the winter cold. By 9, the engine room had fallen silent. The massive triple-expansion engine that powered the rolling mill sat motionless, its flywheel locked in place, its steam lines drained and vented. The boilers in the adjacent building were banked low, maintaining just enough pressure for morning startup. Inside the engine room, the temperature dropped steadily as the residual heat from 12 hours of operation leaked through the brick walls and iron roof trusses. Thomas Brennan made his first round at 10:30. He carried a kerosene lantern and a logbook, walking the same route he had walked for 3 years. He checked the bearing temperatures with the back of his hand, inspected the governor weights for unusual wear, and noted the position of every valve and regulator in the room. Everything was in order. The main steam regulator, a brass and iron assembly mounted on a vertical pipe near the engine throttle, was closed tight. Its handwheel was locked in place with a pin. The position indicator showed 0 flow. Brennan recorded this in his log and moved on. At midnight, he heard it, a faint hiss, steady and low, coming from the direction of the engine. Not the sharp crack of a ruptured line or the roar of an open valve. Just a whisper of steam, barely audible over the creaking of cooling metal. Brennan stopped in the doorway and listened. The sound persisted. He raised his lantern and walked toward the regulator. The handwheel had not moved. The locking pin was still in place, but the position indicator had shifted. The needle, which had pointed to 0 an hour earlier, now rested just past the first graduation mark. The regulator was open, not fully, not dangerously, but open enough to allow a thin stream of steam to escape into the room, condensing into a faint mist in the cold air. Brennan set down his lantern and placed his hand on the valve body. It was warm but not hot. The handwheel resisted when he tried to turn it, as though something inside the mechanism was holding tension. He removed the locking pin and carefully rotated the wheel clockwise, closing the regulator. The hiss stopped. He replaced the pin, recorded the event in his log, and continued his round. When he returned an hour later, the regulator was still closed. By morning, the day shift found everything in its proper position. No one mentioned the incident. Brennan assumed he had misread the indicator during his first pass, but the next night it happened again. The second occurrence was identical. The regulator, closed and locked at the start of the shift, was found slightly open near midnight. The position indicator showed the same small displacement. The hiss of escaping steam was just loud enough to be noticed in the quiet room. Brennan closed the valve again and made a note in the logbook, this time adding the time and temperature. The engine room had cooled to 48 degrees. He wondered if the cold was affecting the valve somehow, though he had no clear explanation for how that might happen. The chief engineer, a man named Arthur Calhoun, reviewed the logbook on Friday morning. He had worked in steam plants for 20 years and had seen valves fail in every conceivable way. Packing glands wore out, springs broke, stems bent under pressure, but a regulator that opened itself, only at night, and only slightly, was something new. He walked to the engine room and examined the valve assembly. The external components showed no signs of damage. The handwheel turned smoothly. The stem moved without binding. The packing was tight. He instructed Brennan to monitor the valve more closely and to record the exact time of each event. Over the next week, the pattern held. Every night between 11:30 and midnight, the regulator opened by the same small amount. By morning, it had closed itself. No human intervention. No obvious mechanical failure. The behavior was predictable enough that Brennan began to anticipate it. He would stand near the regulator at 11:45, lantern in hand, and wait for the hiss to begin. It always did. The needle on the position indicator would creep forward, slowly and steadily, until it reached the first graduation mark. Then it would stop. The steam would escape for a few hours, and by dawn, the indicator would return to 0. The regulator sealed itself as reliably as it had opened. Calhoun brought in 2 senior engineers from the maintenance department. They disassembled the regulator during a scheduled shutdown, laying out every component on a clean workbench. The valve seat was smooth. The stem threads were intact. The spring that provided the closing force was within specification. They reassembled the valve, tested it under pressure, and found no deviation from normal operation. When they asked Brennan to describe what he had seen, he could only repeat the same facts. The valve opened at night, after the room had cooled, and closed by morning. The engineers had no explanation. The behavior continued through the winter. Brennan's logbook entries became a detailed record of the regulator's movements. He noted the time of opening, the ambient temperature, and the time of closure. The pattern was consistent. The regulator opened when the room temperature dropped below 50 degrees. It closed when the temperature rose above 55 degrees, which typically occurred after the boilers were brought up to pressure in the morning and residual heat began to fill the space. The correlation was unmistakable, but the mechanism remained unclear. Other night watchmen began to take notice. A man named Dietrich, who worked the adjacent boiler house, mentioned that he had heard the same hiss during his rounds. He assumed it was normal. A machinist named Kowalski, who occasionally worked late shifts, said he had noticed the position indicator moving once, but thought he had imagined it. The regulator's behavior had been occurring for weeks, possibly months, before anyone paid attention. It was subtle enough to be dismissed as a misreading or a minor anomaly. Only Brennan's methodical documentation made the pattern undeniable. Calhoun decided to observe the regulator himself. On a cold Tuesday night in February, he stationed himself in the engine room with Brennan. The room was silent, except for the occasional groan of contracting iron. At 11:40, the hiss began. Calhoun watched the position indicator. The needle moved slowly, almost imperceptibly, until it reached the first mark. He placed his hand on the valve body. It was cool to the touch. He tried to turn the handwheel, but it resisted. The resistance was not the smooth friction of a well-lubricated mechanism. It felt uneven, as though something inside was binding and releasing in small increments. He left the valve open and waited. By morning, the needle had returned to zero. The valve had closed itself without any external force. Calhoun wrote to the valve's manufacturer, a firm in Pittsburgh that specialized in industrial regulators. He described the behavior in detail and requested technical insight. The response came 3 weeks later. The engineer who replied acknowledged that thermal effects could influence valve position, but suggested that the movement Calhoun described was too large to be explained by simple expansion and contraction. He recommended checking for worn components or improper installation. Calhoun had already done both. He was left with a valve that worked perfectly under normal conditions but behaved autonomously at night. A mechanical regulator is a device designed to hold a fixed position until commanded to change. In a steam system, the regulator controls the flow of high-pressure steam from the boiler to the engine. The operator sets the desired flow rate by turning a handwheel, which raises or lowers a valve stem. The stem moves a disc or plug against a seat, restricting or allowing flow. A spring inside the regulator provides the force needed to keep the valve closed when no steam pressure is acting on it. The spring is preloaded during assembly, meaning it is compressed to a specific tension that corresponds to the valve's design parameters. In theory, once the handwheel is set and locked, the valve should remain in that position indefinitely. The spring force and the geometry of the linkage are calculated to resist movement caused by pressure fluctuations, vibration, or minor temperature changes. The valve seat is machined to a tight tolerance, ensuring a positive seal when closed. The stem and handwheel are threaded, so any movement requires rotational force, not just linear displacement. The locking pin prevents accidental rotation. Every element of the design is intended to create a stable, predictable system. But stability in a mechanical system depends on more than just design. It depends on the constancy of the environment. Materials expand and contract with temperature. Lubrication thickens in the cold and thins in the heat. Friction between sliding surfaces is not constant. It varies with load, speed, and surface condition. Springs lose tension over time, and the amount they lose can change with temperature. Linkages that appear rigid when warm can develop small amounts of play when they cool. These effects are usually negligible. In most cases, they are absorbed by the tolerances built into the system. But in rare configurations, they can combine in ways that allow a valve to move on its own. The regulator at the Cambria Iron Works was not defective. It was responding to a set of conditions that its designers had not anticipated. The valve had been installed in a room that underwent large temperature swings. It had been in service for several years, long enough for certain components to wear in ways that were not immediately visible. And it had been set to a position where the forces acting on the stem were nearly balanced, meaning that even a small change in friction or spring tension could tip the balance in favor of movement. Understanding what was happening required more than inspecting the valve. It required reconstructing the sequence of events that occurred each night as the room cooled and the forces inside the regulator shifted. Calhoun began a more detailed investigation. He installed a thermometer near the regulator and recorded the temperature every hour throughout the night. He measured the room temperature, the temperature of the valve body, and the temperature of the steam line. The data showed that the valve body cooled more slowly than the surrounding air, but faster than the steam line, which retained heat from the banked boilers. By midnight, the valve body had dropped from 90 degrees to 55 degrees. By morning, it had risen back to 65 degrees as the boilers were brought up to pressure. He also examined the valve's internal components more carefully. The spring was made of tempered steel, a material chosen for its ability to maintain tension under load. But steel's elastic properties change with temperature. As the spring cooled, it contracted slightly, reducing its effective preload. The reduction was small, only a fraction of a pound, but it was enough to weaken the closing force acting on the valve stem. At the same time, the valve stem itself was contracting. The stem was made of iron, and the linkage that connected it to the handwheel was made of brass. Iron and brass have different coefficients of thermal expansion. As both materials cooled, they contracted at different rates, creating small changes in the geometry of the linkage. Calhoun also noticed something unusual about the handwheel's movement. When he tried to turn it during the day, it rotated smoothly with consistent resistance. But at night, after the room had cooled, the resistance felt uneven. The wheel would turn easily for a fraction of a rotation, then suddenly resist, then release again. The pattern repeated every few degrees of rotation. He suspected that this was due to friction in the threaded connection between the handwheel and the stem. The threads were lubricated with a thick grease that stiffened in the cold. As the grease thickened, it created pockets of high and low friction along the threads. This is known as frictional hysteresis, a condition where the force required to move an object depends on whether it is moving or stationary. During the day, when the room was warm and the grease was fluid, the friction was low and evenly distributed. The spring could easily hold the valve closed. But at night, when the grease thickened and the spring weakened, the friction became uneven. The valve stem would stick in place until enough force accumulated to overcome the static friction. Then it would slip forward slightly, release some of the stored elastic energy, and stick again. Over the course of an hour, these small slips added up to the visible movement of the position indicator. The final clue came from the valve seat itself. When Calhoun removed the valve again, he noticed faint wear marks on the seat, indicating that the valve disc had been moving slightly during operation. The marks were not deep enough to cause a leak, but they suggested that the disc was not sitting perfectly flat against the seat. The slight misalignment created a small gap, which allowed steam to escape when the valve was nominally closed. The gap was only visible when the components were cool and contracted. When the room warmed up and the components expanded, the gap disappeared and the valve sealed itself. Calhoun and his team spent several weeks analyzing the data. They built a detailed model of the regulator's behavior, starting with the moment the engine was shut down and the room began to cool. At that point, the valve was closed and locked. The spring was providing a steady closing force. The threads were well lubricated. The valve seat was sealed. Everything was in equilibrium. As the room cooled, the first change was in the spring. The steel contracted and the preload decreased. The closing force dropped from 50 pounds to 48 pounds, a small change, but measurable. At the same time, the valve stem and linkage began to contract. The iron stem shrank slightly, and the brass linkage shrank at a different rate. The result was a small shift in the geometry of the connection between the handwheel and the stem. The shift was less than 1/1000th of an inch, but it was enough to change the angle at which the stem pressed against the valve seat. The new angle reduced the effective closing force by another fraction of a pound. Meanwhile, the grease in the threads was thickening. The viscosity increased, and the friction became uneven. The stem began to stick in place, held by static friction, but the spring was still trying to close the valve, and as the spring contracted further, it stored elastic energy. The energy accumulated slowly over the course of an hour until it reached the threshold needed to overcome the static friction. At that moment, the stem slipped forward. The valve opened slightly. Steam began to escape. The movement was not continuous. The stem moved in small increments, sticking and slipping as the elastic energy was released and then rebuilt. Each slip opened the valve a little more until the position indicator showed the first graduation mark. At that point, the forces reached a new equilibrium. The spring force, reduced by cooling, was just enough to hold the valve in the new position. The valve stayed open for the rest of the night. As morning approached and the room began to warm, the process reversed. The spring expanded and regained some of its preload. The grease softened and the friction became more uniform. The linkage geometry shifted back toward its original configuration. The valve stem, now free to move, was pulled back by the spring. The valve closed itself, sealing against the seat as the components expanded and the gap disappeared. By the time the day shift arrived, the regulator was in its original position. The regulator at the Cambria Iron Works was not malfunctioning. It was responding to a precise combination of thermal, mechanical, and material effects that only occurred under specific conditions. The key factors were thermal contraction, spring preload drift, frictional hysteresis, and linkage geometry. Each factor alone was too small to cause noticeable movement, but together they created a situation where the valve could overcome its own resistance and adjust itself. Thermal contraction altered the dimensions of every component in the system. The valve stem, the spring, the linkage, and the valve body all shrank as they cooled. The amount of shrinkage was different for each material, depending on its coefficient of thermal expansion. The result was a shift in the internal geometry of the regulator. The shift changed the angle at which forces were applied, reducing the effective closing force and making it easier for the valve to move. Spring preload drift compounded the problem. The spring was designed to provide a constant closing force, but that assumption only held true if the temperature remained constant. As the spring cooled, it contracted and lost tension. The loss was small, but it was enough to weaken the force holding the valve closed. In a system where the forces were nearly balanced, even a small reduction in spring tension could tip the balance toward movement. Frictional hysteresis created the conditions for stick-slip motion. The grease in the threads thickened in the cold, increasing the static friction and creating pockets of high resistance. The valve stem would stick in place until enough elastic energy accumulated to overcome the friction. Then it would slip forward, release some energy, and stick again. This process repeated until the valve reached a new position where the forces were once again in balance. The final element was the tolerance stack-up in the linkage. Every mechanical connection has some amount of play or clearance built into it. The clearances are necessary to allow for thermal expansion and to prevent binding. But when multiple connections are linked together, the clearances can add up. In the regulator, the clearances between the handwheel, the stem, and the valve disc created a small amount of backlash. As the components cooled and contracted, the backlash increased. The increased play allowed the valve to move more freely, reducing the resistance to motion. Calhoun documented his findings in a detailed report. He recommended that the valve be replaced with a model that used a different spring material and a different lubricant. He also suggested that the linkage be redesigned to minimize the effects of thermal contraction. The changes were implemented during the next major overhaul. The new regulator did not exhibit the same behavior. But the incident at the Cambria Iron Works served as a reminder that control systems are not truly static. They exist in a state of dynamic equilibrium, responding to forces that are often invisible and poorly understood. A valve that appears stable under one set of conditions can behave unpredictably under another. The difference between control and autonomy can be as small as a few degrees of temperature, a fraction of a pound of spring tension, or a shift in friction that no one thought to measure. The regulator that opened by itself was not haunted. It was not broken. It was simply adjusting to the world around it in ways that its designers had not anticipated. And in doing so, it revealed a truth that every engineer eventually learns. The systems we build are never as rigid as we imagine. They are always moving, always responding, always finding new ways to balance the forces acting upon them. Control is not a state. It is a process. And sometimes, in the cold and the quiet, that process takes a path we did not expect.